Welcome to this recording. Today we will present an article on image acquisition. Image processing is a form of signal processing for which the input is an image, whereas the output is either an image or a set of characteristics or parameters related to that image. This process is done by using algorithms in order to, for example, operate on colors or enhance the image. The most flexible way of doing this is by using digital computers because they can be reprogrammed easily, but most importantly, because they can provide the speed and storage requirements for such algorithms. In the recent years, image processing has grown rapidly thanks to various studies and researches in many different fields. This has led to the establishment of image processing and its application in numerous diversified domains. With the rapid growth in computer performance, one can believe that the importance of image processing will remain over the years and maybe grow even bigger. A digital image is a discrete two-dimensional function f of xy. During the expose, it will be assumed that an image is rectangular and that it is composed of y rows and x columns. Its resolution is written x times y. F of 0, 0 refers to the top left corner of the image, while f of x minus 1, y minus 1 determines the bottom right corner, such as shown in the image. A histogram is a graph of a relative frequency of each pixel value that appear in a grayscale image. It provides a great summary of the intensities in an image. The image mean is the average pixel value of an image. The image variance gives an estimate of the spread of pixel values around the image mean. The entropy is calculated from the histogram. It is denoted h of f and can be calculated using this equation, where PR of z is the probability of occurrence of a symbol z. A uniform histogram will correspond to the maximum value of the entropy, while an image where all the pixels have the same intensity will provide an entropy of value 0. This equation shows how to combine a scalar C and an image G in order to produce a new image F. This is a pixel-wise operation, which means that each pixel in G is operated with C and the result is put in F. This can be used for image enhancement. For example, the left side image uses 8 bits per pixel, but only contains pixels with intensities varying from 64 to 191. This equation will enhance the image by using its full intensity range, providing the right side image. It is also possible to combine two images having the same resolution by using a pixel-wise operation, such as shown in this equation. An example of image-image operation is alpha blending, which consists in the mixing of two images where alpha determines the mixing proportions. This picture shows a blended image of the two previous images where alpha is equal to 0.5. Image acquisition is the process of obtaining a digitized image from a real-world source. Each step of this acquisition may introduce changes in the value of the pixels. These changes are called noise. For example, imagine that someone wants to send a photo via the internet. And standard way of achieving this task is by taking the picture, then printing it, then scanning the printed picture into a computer and finally emailing it. Each step of this process may introduce noise. Indeed, when taking the picture, the lens of the camera may be dusty or the scanner may cause minor pixel misalignment. This shows that an image acquired from the real world is very probable to contain errors.
Now let's talk about image processing algorithms. Gaussian smoothing noise is caused by sensor electronics, and if introduced in signal transmission, it can reduce visual quality of an image. So that's why we use 2D Gaussian smoothing, which is a convolution operation, and a low-level image processing algorithm which will suppress this noise. For this we use a moving kernel, which is a convolution matrix that represents the shape of a Gaussian hump. The pixel intensity is turned into a sum of the product between the intensity values within a neighboring area centered at the pixel and in the coefficient of the kernel. So the fine structure, which are smaller than the filter's kernel size, gets removed. A 2D isotropic Gaussian filter can be seen as product of two 1D Gaussians, as we can see on the slide, where sigma is the standard deviation. As an image is a discrete pixel distribution, we truncate gxy by the kernel at more than about 3 sigma, because practically it's the point at which g's distribution is equal to 0. Like this, we may perform convolution. The effect of this is that the Gaussian smoothing blurs the image. Edges are local variation in image function which are defined by a discontinuity in gray level values and have strong intensity contrast. That's why we'll use canny edge detection, which is an optimal edge detector algorithm that maximizes the probability of detecting true edges while minimizing probability of false edges. It is an intermediate level image processing operation implemented in 4 stages. First, we image smoothing. Then we'll estimate the gradients in x and y direction, gx and gy, for an image, which are given by the smooth image along respectively y and x axis, convolved with Gaussian kernel derivative along the x and y axis respectively. So now the spatial position for thick and blurry edges can be determined correctly. We use non-maximal suppression algorithm to eliminate unnecessary edge pixels in order to make thick edges sharper. For this to be done, the image pixels are grouped in 4 quadrants depending on their gradient direction theta, which we can observe on the slide. Like this, the image edges are labeled and we can delete the pixels which aren't at the local maxima oriented according to theta. Finally, we use hysteresis to track the remaining undeleted pixels and improve edge localization. This method uses a high and low threshold value found from the image statistics and return all the 1 pixels coming from the high threshold and those from the low threshold which are connected to a high threshold value through 8 connected neighborhoods. Most edge detectors work on the grayscale representation of the image. This allows to lower the amount of data to work with because grayscale corresponds to one channel. However, we lose some information, thus we find less edges than the canny color edge detector. Now let's add color component of the image. The edge detector detects edges in region with high color variation, but not low intensity variation. The algorithm for color edge detection is as such. Reads in a color image, divide the image into its 3 separate color channels. Canny edge detector then creates a resulting color edge map for each color channel. We get then more information and thus more edges found than with grayscale version. At the end, we combine the 3 color channels maps into 1 edge map. So now let's talk about digital filters. So if we consider as an input the electrical analog signal containing all frequency components, a high-pass filter will output a signal containing high-frequency components, whereas a low-pass filter will output a signal containing the DC bias and a low-frequency component. However, in imagery, low-frequency components in an image are characterized by slow change in the contrast of values or values of adjacent pixels, whereas high-frequency components are characterized by rapid change in contrast encountered at the edge of an object, for instance, noise such as random speckles. It can be reduced using an averaging low-pass filter, and by using high-pass filter, the effect of the background light would result in a DC bias in the vision system data, since the minimum value of all pixels will be above some given value.
Now we will talk about imaging hardware. First of all, CCD sensors are made up of light-sensitive pixels that produce an electrical charge proportional to the received light intensity. They are usually arranged in a single line or in a 2-dimensional grid. After that, there are CMOS sensors, of which there are generally 2 types, active pixels and passive pixels. Passive pixel devices have charge amplifiers below each pixel column, while each active pixel has a charge amplifier. Each of the line selectors are synchronized sequentially. This allows each switching transistor or charge amplifier in each row to turn on and transfer each pixel's charge to the column outputs. A color filter matrix is a mosaic of colored filters on the photosets, separating the colors into a variety of red, blue, and green pixels. It is possible by interpolation to know very accurately the color of each sensor by looking at the pixels in the area. The most common model of filter is the Bayer filter pattern with 50% of green filters, 25 of reds, and 25 of blue. The advantage is that this method requires only one sensor and that all the information of color is recorded at the same time. Digital image processing is a form of signal processing whose input is an image and returning as output an image or features. Often, these techniques involve treating the image as a 2-dimensional signal and using standard signal processing techniques. Three models of colors are used for the treatment of the digital images: the RGB color model for monitors, the CMY for printing, and the HSI, also used for monitors and to separate the information relating to the gray levels and color. However, each photo site is colorblind and only keeps track of the total intensity of the light that reaches the sensor. The solution is to capture the three primary colors separately and combine them to create the full spectrum. An image file consists of pixels, vector data, or both together. These files are then rasterized into pixels when displayed on the screen. There are three categories of image formats: raster, vector, and stereo. Images can again be processed with softwares of several levels. There are those of low level. The input and output are both images and allow to reduce noise, improve contrast, and make the image sharp. Then there are those of medium level. The input is an image, but the output is extracted attributes in order to segment, classify, or correct the colors. Finally, those of high level. The software gives meaning to the image by doing tasks related to vision or image recognition. Now, how to represent the image. A frame buffer contains a 2D array of numbers representing the intensities. The screen creates a continuous light image from these discrete numerical values. It is also important to understand that a pixel is not a small square of light next to its neighbor, but rather a point sample.
Now I will present you the last part of this paper, which is the processed image quality. But first, how can we define an image quality? According to the International Imaging Industry Association, image quality is the perceptually weighted combination of significant attributes, contrast, graininess, etc., of an image when considered in its marketplace or application. So it means that the quality of an image depends on its function and goal in a specific application field. But this definition has two issues. Firstly, it doesn't consider the common aspect of quality dependencies, and secondly, it doesn't assume that the image receiver could be a human, but it could be a computational system. So it makes more clear the link between image generation process and image quality assessment. But how quality assessment is done? It could be done by one or more methods. In a subjective way, such as psychophysical experiments involving human observers, and in an objective way, such as quantifying the performance of an image-based task done by the computational system. Or another method is to assess the performance of the imaging device on target images using software tools. Above the image quality dependence, the first one is of course the human eye perception that will detect the photons of light. Light travels in straight lines, so visual information can be used to determine the direction and the distance of an object. But sometimes some images will create a wrong perception in our brain, such as these illusions. The first image, when you look at the white point, you could see the other points become suddenly black. And the second image, you could believe that the lines are diagonal, but in fact, they are not. This is the phenomenon of lateral inhibition, where each neuron will influence its neighbor. Another image quality dependence is the processing hardware with the CCD architecture, which is a new architecture of pixel interleaved array, PIA, in order to maximize the space by rotating the pixel by 45 degrees. So the resolution will be 1.4 times higher in the PIA CCD in horizontal and vertical directions. So here we can easily see the details on the PIA CCD image, but not on the right one. In conclusion, image quality is a function of object environment such as type of scene geometry, lighting conditions, etc. Function of processing hardware architecture such as imaging device, image processing and transmission system, and a function of human perception, such as observer adaptation state, viewing conditions, and expectations. Thank you for listening.